Hello, we are going to explain today the 14th lesson of the course, 4th of the present section 3, entitled this lesson, Attenuation and Absorption of a Wave, in which we are going to present the following sections. How intensity decreases with distance, what is attenuation, what is absorption, and compare them and how absorption is characterized from a parameter called absorption coefficient. We've all experienced, for example, with sound, how intensity decreases with distance. For example, here we have Jota, very close to a loudspeaker that is sending music or emitting music. We have Amanda, and as we all know, you can hear it much closer than from far away. Up close, well, here we have Jota absolutely agitated because he is going deaf, and Amanda in the distance tuning her ear and paying attention to see if she picks up something. Why does the intensity decrease with distance? We already know one of the phenomena that causes this process, attenuation, which is the decrease in intensity of a wave as the energy is spread over wider and wider fronts. For example, at a given moment, 50 joules are emitted from a source, 50 joules pass through the next front, 50 joules pass through the next one, the 50 joules remain, but they are distributed over a wider and wider area, and therefore touch less and less energy density and less intensity. The second cause we are going to discuss in this lesson is absorption, the decrease in intensity of a wave as it loses energy while propagating. This is due to interactions with the medium, such as, for example, friction in waves, heat losses, absorption, and emission of light by molecules, and so on. The fact is that the energy that the wave ends up having decreases from one front to the next. For example, if we started with 50, then the next one can have 40, the next one 28, and so on and so forth. So there is a loss of energy. We are going to visualize this with several virtual laboratories. In the first one, we are going to use the economic analogy that we already presented in the previous lesson. We are issuing, in this case, 16 coins called joules, the joule coin of the country of energy. And it's going to travel to the right. And then we have that, they keep coming to the next front. We have 2 joules for each J, 2 joules per meter, assuming that each J represents 1 meter of front, and here we still have 2 joules per J. So this is a case where we have neither attenuation and absorption. But let's see what happens if we still have no attenuation, since there is no increase in the size of the fronts, but there is absorption, and we will see the effect. The effect will be as if it is no longer a question of distributing the money among more or less people. It is that there is the revenue service with its taxes on transport or trade, and as the coins travel, it keeps a part of it. Let us say that for each one of these trips from front to back, it keeps 50%, so this will happen, simulating it. As the coin is losing money, we activate the attenuation option. We will see how we are left with half the money, that is J. Each J does not receive now 2 joules, but 2 half joules, 1 joule per J, 1 joule per meter. If the question follows, let us remember that taxes do not work on, that is, they are not fixed amounts, they are percentages of, so if you take 50% now, you will take 50% of what is left. So not the rest of the coin, but half of the coin that is left. So each J gets 2/4 of a joule, half a joule per J, half a joule per meter. Let's see the same effect, but now with one that is providing energy at a constant rate directly. We see, looking at the effect in question, you can notice how, since what is removed is by percentage of what was there, it is removed faster at the beginning, since it is removed on the whole coin, and each time it is a slower evolution. You can also see how past J, the second J keeps decreasing. That was a case of only absorption without attenuation. Here we are going to see now a case where we have both attenuation and absorption. We start with attenuation only. The coins come out, 24 coins, 24 joules. And here we have that each J has 2 joules. There are 2 joules per J, 2 joules per meter. Here, as there are more J's, because the front is longer, they result in 1 joule per J, 1 joule per meter. But what happens if, in addition to attenuation, we also have absorption acting, as in the case of straight fronts? Well, as we can see, each J still receives 2, but not 2 joules, 2 half joules. There is 1 joule per J, 1 joule per meter. And the subsequent J's get 1 joule, but only 1/4 of each. So each one has 0.25 joules per jack, 0.25 joules per meter. The same effect simulated with a continuous wave or providing energy at a continuous rate would be this right here. I activate the absorption and we can see how it's steadily decreasing as the spare is being supplied, which in turn continues to be affected by that same absorption. So we have both absorption and attenuation. Here we have the example applied to a linear surge. We already know the situation where an unchanging energy travels, and therefore we have, for example, that the wave heights are constant. Recall that the amplitude goes with the square root of the intensity of the amplitude and of the energy, And this, if we also have absorption, we can see not only that at each point there is a lower height than at previous points, but as we see physically how each wave is losing height as it loses energy. This would be waves subject to absorption, but not attenuation. If we have both, we can see it, for example, in this case in circular front waves. We have how the amplitude decreases with distance. But if we also add the effect of absorption, the decrease is even more pronounced. In the case of light, we can see the situation in which we have neither absorption nor attenuation, which would be this one here, since the propagation is in a straight line with flat fronts. Here I can also, however, add the effect of absorption, and we notice as it propagates and ends up stabilizing how we see J getting darker and darker because the intensity decreases with distance. Here you can hardly see him, and well, if I put this in the extreme case, you can hardly see him at all. In the case of spherical fronts, for example, those emitted by a light bulb or a lamp, we will remember how the intensity decreases with distance due to attenuation, because the energy is maintained, but it is distributed among wider and wider fronts. But if I also add the effect of absorption of energy losses, we can see what is happening, that each time as the absorption increases, it looks worse, and then in this limiting case, there is practically no J, or it is not seen. It may seem that the white is more intense than before. That is an optical effect, because it is the same color code. Finally, in the case of sound emitted by a membrane in a spherical shape, this is the situation in which we are going to see now when we have attenuation, since it decreases with the square of the distance, the intensity, and therefore with the distance, the amplitude, and we see how the molecules that are farther away move in this visualization. If I also add absorption, i.e. that sound energy is lost as it travels, we can see that they move quite a bit slower. How can we mathematically characterize the absorption of attenuation? We were talking when we looked at formulas like I equals P divided by 4PR squared. Well, since the case where we have both phenomena attenuation and absorption at the same time is much more complex, let's assume that there is no attenuation, that is that the fronts always measure the same. Therefore, they are one-dimensional waves or two-dimensional waves of straight fronts or three-dimensional waves of flat fronts. In that case, what happens? That the only reason for the decrease of the intensity is absorption, and it happens in the following way experimentally, that in a very small distance, differential of x, the intensity of the wave becomes I plus its differential of increase. What happens is that, of course, as what you do lose, the differential of increase is negative due to absorption. The fraction lost minus the differential of I. That is, as the change of sign is the loss in percent per one, is proportional to the distance traveled. The longer the distance, the more loss there is. It seems reasonable. It is like the compound interest of the banks, or what they give us instead of what they take from us. Well, if it's not a loan, obviously. So we have this linear relationship or changing signs, this one here. Well, this beta parameter is called the absorption coefficient, and it characterizes the rate at which energy is being lost. Of course, if it's zero, there's no loss. The larger it is, the more you lose. The unit, it seems obvious, since the term on the left is a coefficient of an intensity differential, split by itself is dimension 1, and on the right then, differential of x is meters, so that everything fits. Beta has to be meters to the minus 1. That is the SI unit of the absorption coefficient. Well, that is what is called a differential equation in mathematics, which probably many of you are not able to solve, and that is to find a function that satisfies this equation. I am going to give the solution, although there are methods to obtain it mathematically, and it is this. The intensity is equal to the starting intensity times the exponential of minus the absorption coefficient times x. If it can be checked, although we do not know how to obtain it, that it is true, you can check that in the x equal to 0, substituting x equal to 0, I get that the intensity is indeed the initial one. And we can check by differentiating differential is equal to the constant by the exponential itself by the derivative above, by differential of x, that if I make this quotient and replace differential of y by this expression and y itself by this other, practically everything is simplified, and I have less differential, less b differential of x, which is the starting equation that we had to fulfill. It is interesting here to talk a little about what is special about exponential functions in general. For example, here we have an increasing exponential curve. It can be from the xe to the 2xe to the 1.5x. What is fundamentally special about it is that if it doubles in a certain section, green length that you see here, what it takes to double, that is, to make a geometric progression. If it were arithmetic, it would be a straight line. To double that value, as you see here, it takes the same time. And to duplicate the new value, it takes the same, that is, at constant times or constant distances, we have 1, 2, 4, 8. A decreasing exponential works exactly the other way around. It simply multiplies by a number less than 1 each time. For example, if we start with a value, it decreases by half in one time, half of that half in the same time, half of the half in that same time or distance, depending on what x is. For example, decreasing exponentials, if it is the minus x and the minus 2 comma minus 2x, both have their interests. For example, the first one is the one that would have, for example, a population of rabbits that the population will increase at a rate that is given by the population itself. Logically, if 100 rabbits give me 110, 200 give me 220. Well, this would result in a decreasing exponential curve, so the fact that the rabbit population, if it gets out of control, grows exponentially is not a way of speaking, it is mathematical. As decreasing exponentials then, you have one that you have already seen in this course, as is the decrease of amplitude in harmonic movements in which there are energy losses. Or, for example, so my radioactive decay, or this case that we are seeing here. In fact, it can be verified that always what takes the intensity to become half is a quantity, a fixed distance that we call of a medium. Well, if we have a certain distance x, there is an intensity, and we want to know at what distance from there. We have the half, we only have to do the development substitute, and you can easily check that I have a result that does not depend on x, which is fixed. In fact, clearing, we can check that this distance is logarithm of 2, logarithm of both of 2, due to the beta. If beta is 0, the distance is infinite because it never becomes half, it remains. The larger the absorption coefficient, the less length we have half, the faster everything is lost. One last example to see a practical case of this whole story. You will remember that we already saw how, as the sun was higher, it turned out that the normal surface was larger, and therefore we had more power received. And I already commented that the intensity also grew. Why? We have here an exaggerated clue, but let's say we have an atmosphere like the one you see there, surrounding the Earth, and the sun is at the zenith. That day is exactly noon, at a point where they also set perpendicular, which is a place that would have to be between the tropics. It can't happen, for example, outside them. Well then, let's admit that the atmosphere is 30 kilometers long. In reality, it is much longer. I think it is about 1,000 and some, but in the first 30 kilometers is 95% of the air, and as the matter is what makes the light lose by absorption. Let's stick to this part to be able to compare. What happens when it is dawn or dusk, nightfall, that the sun is above, it's right on the horizon, and therefore it's in this position or in the symmetrical one on the left. If you look at it, it has to go through the same layer of atmosphere, but with a much longer length. This one here, and how long is it? It is a fairly simple calculation. If we consider that this is the radius of the Earth in kilometers, this is the same radius of the Earth, plus the thickness of the air is the new distance, and that here we have clearly a right triangle. Just apply Pythagoras and check that sunlight has to cross, when dawn or dusk, 619 kilometers instead of 30. This is an estimated value, but to give you an idea that the absorption, since it depends on the length, is much higher. That is why sunlight is more intense the higher it is. In reality it is the same, but it reaches us more intense the higher it is because it has to pass through shorter atmospheric lengths. And this is the summary of today's lesson. Thank you very much for your attention.